Right now, on a machine with 25 gigabytes of RAM and no graphics card, a 744 billion parameter AI model is answering questions. That sentence should be impossible. That model, squeezed down to 4 bits, is about 370 gigabytes on disk. It does not fit in that machine's memory. It never will. And it's running anyway, in pure C zero dependencies, built by a single developer. The project is called Colibri, Italian for hummingbird, and it has pulled over 17,000 GitHub stars in 3 weeks because it quietly breaks the rule everyone believed about local AI. The rule was, if the model doesn't fit in your memory, you can't run it. Colibri's answer is one sentence. And once you hear it, you will never look at your hardware the same way again. The model doesn't need to fit, it needs to be placed. In this video, I'll show you exactly how that works, what speed you can honestly expect on your machine, and how to set it up yourself. Let's go. First, feel the size of the wall this thing walks through. GLM 5.2 is a mixture of experts model from z.ai. 744 billion parameters, even compressed to 4-bit precision. The weights take about 370 gigabytes on disk. Your machine has what? 16, 32, maybe 64 gigabytes of RAM? That model is more than 10 times bigger than the memory in most desktops. And every other local AI tool solves this the same two ways. Either shrink the model until it fits and quietly lose quality, or tell you to go buy a stack of GPUs. Colibri does neither. No smaller model, no quality cut, no new hardware. It changes the question instead. What if the model never had to be in memory at all? At least, not all of it at once. Here's the insight the whole engine is built on. A mixture of experts model doesn't use itself all at once. Inside GLM 5.2, there are 19,456 small specialist networks, the experts. For every single token it generates, a router picks just a handful of them. So out of 744 billion parameters, only about 40 billion are actually active per token. And it gets better. Most of that active set, the attention layers, the shared experts, is the same for every token. The part that actually changes from one token to the next is only about 11 gigabytes of experts. Read that again. A 370 gigabyte model, where the moving part is 11 gigabytes. That is not a model that needs a supercomputer. That is a model that needs a librarian, something that knows which experts to have ready and where everything else can wait. So instead of asking, does it fit? Colibri asks, where should each piece live? The model doesn't need to fit. It needs to be placed. So Colibri treats your whole machine as one memory hierarchy. 3 shelves. The top shelf is VRAM. If you have a GPU, it's the fastest shelf and the smallest. The middle shelf is RAM, fast and modest. The bottom shelf is your SSD, huge and slow. Every other runtime treats that bottom shelf as failure. If you touch the disk, you've already lost. Colibri makes it a first-class citizen. Here's the placement. The dense part of the model, attention, embeddings, the shared experts that every token uses, about 17 billion parameters, is quantized to 4 bits and sits permanently in RAM. That's just 9.9 gigabytes resident. And the 19,000 routed experts, each one only about 19 megabytes, live on the SSD, all 370 gigabytes of them, and get streamed in the moment the router asks for them. That's the whole trick. Nothing is shrunk. Nothing is skipped. Every expert keeps full fidelity. Some just answer from a slower shelf. And the entire engine doing this is essentially a single C file. No Python at runtime. No frameworks. Zero dependencies. Now watch what happens for every single token on every single layer. 5 steps. The same path every time. Step 1. Root. The router looks at the token and picks which experts this layer needs. Step 2. Union. If the engine is working on several positions at once, it merges their lists so each unique expert is fetched exactly once, not once per position. Step 3. Place. For each needed expert, is it already on the GPU? Is it in RAM? Or is it on disk? Best available shelf wins. Step 4. Overlap. The experts that are already resident start computing immediately, while the missing ones load in the background. Compute and disk reads happen at the same time. And step 5. Learn. The engine writes down which experts were used, because that memory is about to become your speed. Route, union, place, overlap, learn. And here is the rule that makes all 5 trustworthy. Placement only ever decides speed, never precision, never which experts answer. A slow shelf can cost you seconds. It can never cost you quality. Of course, reading experts off a disk is the expensive part. So nearly all of Colibri's cleverness serves one obsession. Never wait for the disk twice. 4 moves. Move 1. Each expert's 3 weight matrices are stored adjacent on disk. So fetching an expert is one single read, not 3 seeks. Move 2. An asynchronous I/O pool loads missing experts, while the resident ones are already computing. The CPU almost never sits idle. Move 3. Batch union. When several positions need overlapping experts, each unique expert crosses the disk boundary exactly once. And move 4 is my favorite, the pilot. A look-ahead thread watches the router and prefetches the experts the next layer will probably want. And here's the wild, measured fact that makes it work. Expert routing turns out to be 71.6% predictable, one layer ahead. Before a layer even asks, most of its experts are already on their way up. The result? What looks like a disk-bound problem starts behaving like a pipeline. The disk feeds the next step while the CPU chews the current one. And then there's the part that makes Colibri feel almost alive. It learns you. Between the fast shelves and the slow shelf sits a learning cache. Every turn, the engine records which experts your workload actually routed to into a small usage file. And it pins the hottest ones, your hottest ones, permanently into RAM. Think about what that means. The experts a lawyer's documents light up are different from the experts a Python programmer lights up. So the engine literally reshapes its memory around your work. Day 1, cold cache. Lots of disk reads. A week in, the experts you use most never touch the disk at all. Colibri gets measurably faster the more you use it. Same hardware, same model. It just knows you now. Quick 30-second pause, because that learning cache is accidentally the best description of this channel I've ever found. The engine keeps what earns its place and pins what gets used. You can do the same thing right here. Real talk. 90% of you watching haven't subscribed. On Facebook, subscribe is the supporter button. That is what keeps the lights on here. On YouTube, it's free and it tells the algorithm to send you more. Subscribe to support us. And if these deep dives are already earning their place in your week, there's a join button on YouTube too. Members keep this channel independent. Pinned? Good. Back to the engine. Because now I have to prove none of this costs quality. Because right now, you should be skeptical. Surely, all this streaming and caching degrades the model somehow. Here's Colibri's answer, and it's the most rigorous line in the whole repo. The forward pass is validated token exact against the reference transformers implementation. Teacher forcing 32 tokens out of 32. Identical. Not close. Identical. the exact same tokens the reference produces. Placement decides speed only. That's not a slogan, it's a test in the repo. And the same discipline shows up in how it remembers conversations. GLM 5.2 uses a compressed attention state, 576 numbers per token, instead of 32,000, 57 times smaller. Colibri persists that state to disk, so when you close a conversation and come back tomorrow, it reopens warm. Byte identical to a session that never ended. No rereading the whole chat. Here's the sentence to remember. Your machine is slower than a data center. It doesn't have to be dumber. There's one more speed trick, and it comes with the most valuable gotcha in the whole project. GLM 5.2 ships with a built-in draft head, a small module that guesses a few tokens ahead, and the main model verifies the guesses in one batched pass. When it works, you get 2 to nearly 3 tokens per forward pass. Almost free speed. But here's what the Colibri community found the hard way. In issue number 8. Quantize that draft head to 4 bits, like everything else, and acceptance collapses to nearly 0. The drafts are always wrong. The verification always fails. And speculation silently becomes pure overhead. The fix. The draft head must stay at 8 bits. The repo even lists the exact file sizes to check, so you know your download is the right one. And I love that this is documented, because it's the difference between a demo and an engineering project. They measured, it failed, they found out why, and they shipped the rule as a default. The honesty goes further too. The docs straight up tell you, if speculation doesn't pay on your machine, turn it off. So, the question you've been waiting on. What speed do you actually get? I respect this repo enormously for publishing honest numbers. So here's the real ladder. Bottom to top, the floor. A 25GB RAM dev box, everything streaming cold from disk. 0.05 to zero point 0.1 tokens per second. That's one token every 10 to 20 seconds. Painful. Real. And also the proof that the impossible configuration works at all. That's the machine this project was born on. Step up, a 128GB desktop, CPU only, warm cache, about 1.8 tokens per second. Genuinely usable for the questions you'd rather not send to a cloud. A single mid-range GPU like a 5070 Ti laptop class box, just over 1 token per second, with the GPU resident pipeline. And the top, 6 RTX 5090 cards, every expert resident, disk out of the picture entirely. Nearly 7 tokens per second on a 744 billion parameter model at home. Now notice the beautiful part. Same engine, same weights, top to bottom. The hardware only changes where the experts live. That's the payoff of placement. Your next upgrade doesn't unlock the model. It just moves experts to a faster shelf. Let's get it on your machine. 3 steps. Step 1. The model. There's a pre-converted 4-bit container on Hugging Face, linked in the repo and in my description. One warning, and you already know why. Grab the version with the 8-bit draft heads. It says so right in the name. Step 2. The build. Clone the repo, go into the C folder, and run setup.sh. It checks your compiler, builds the engine, and runs self-tests. No package managers. No dependency hell. It's C. And on Windows, it's even easier. There's a pre-built binary in the releases. Download, unzip, run. Step 3. Run it. Point the coli model variable at your model folder and run coli chat. But before you commit hours to downloading, 2 commands will save you pain. Coli Doctor is a read-only readiness check for your machine. And Coli Plan shows you exactly how the engine would place the model across VRAM, RAM and disk before you run anything. Then, when you want more than a terminal. Coli Serve gives you an OpenAI compatible API. So anything that talks to OpenAI can talk to your local 700 billion parameter model. And Coli Web adds a dashboard, which deserves its own moment. Because this might be the most beautiful part of the project. Run Coli Web, open your browser, and you get a live dashboard. Tokens per second, time to first token, and a tier bar showing how much of the model is answering from VRAM, from RAM, and from disk live. But then there's the brain page. All 19,000 experts rendered as a living cortex. The color of each dot is the shelf that expert lives on. The brightness is how hot it's been routing. And every expert used in a turn flashes as it fires. You are literally watching the learning cache do its job, watching the model reorganize itself around you. And the Atlas page goes further. A 3D galaxy of measured expert specialties, where thousands of characterized experts cluster by topic. Poetry here, SQL there, Chinese over there. That's not a marketing render, it's a measurement of where knowledge physically lives inside the model. Spinning in your browser, served from a C binary. And here's the part of this story I can't let go of. This didn't come out of a lab with a GPU cluster. Colibri started as one person on a 12-core laptop with 25 gigabytes of RAM, refusing to accept that the interesting models were for other people's hardware. The name is the thesis. A hummingbird weighs a few grams and visits 1,000 flowers a day. This engine keeps a 744 billion parameter giant alive on hummingbird rations. So here's the identity shift I want you to take from this video. The ceiling on local AI was never really your hardware. It's placement. There are people waiting for GPUs to get cheaper, and there are people learning how memory hierarchies actually work. Only one of those groups is running giants at home this year. If you want to try this yourself, I've packaged everything from this video into one clean PDF. The Colibri playbook. The exact setup commands for Linux, Windows, and Mac. The 8-bit draft head check. The full honest speed ladder. So you know what your hardware will do before you download 370 gigabytes. And the tuning knobs that matter. Explained in plain English. Comment the word Colibri and I'll send it to you free. If you're just getting started with AI coding tools, I've also written step-by-step beginner guides. Links in the description. And I post quick AI moves every day on Instagram and Facebook, while the full deep dives live here on YouTube. All credit for this engine goes to its developer. The repo is linked below. Go start it. And if you run it, open an issue with your benchmark numbers. Because community data points are literally what moves this project forward. Your homework is one command. Coli Doctor. It costs nothing, downloads nothing, and tells you exactly where your machine stands. Say it with me one last time. The model doesn't need to fit. It needs to be placed. Colibri, go.